Chapter 1.3, Combining Transformations, Part 2, Writing Equations from Graphs. To write the equation of a transformed function based on the graph, locate key points on the graph of f of x and their corresponding points on the graph of g of x. Use these points to figure out the value of the parameter a, b, h, and k. Example, the graph of y equals g of x represents a transformation of y equals f of x. Determine the equation of g of x in the form y equals a f bracket b bracket x minus h close bracket plus k. So f of x is our original function and g of x is our transformed function. We need to figure out each of the parameters, starting with stretches and reflections and then translations. I'm going to start with a vertical stretch factor. For f of x, the distance between the lowest point and the highest point on f of x is 4 units. And on g of x, the distance between the lowest point and the highest point is 10 minus 2, which is 8 units. So we go from 4 units to 8 units, which means we multiply by 2. Therefore, our vertical stretch factor is 2. Do we have a vertical reflection? No, we don't, because f of x opens upward and g of x also opens upward. Since they open the same direction, there is no vertical reflection. Therefore, a is positive. We put these two things together, vertical stretch factor of 2 and a is positive. So a equals 2. Next, for the horizontal stretch factor, the distance between the top 2 points is 8 units. On the transformed function, the distance between the top 2 points is 2 units. So we go from 8 units to 2 units, which is multiplying by 1 over 4 or dividing by 4. Therefore, our horizontal stretch factor is 1 over 4. Then do we have a horizontal reflection? If we look at the original function, the function has a vertex at the origin and is symmetrical about the origin. So if we reflected it across the y-axis, it would still look exactly the same. So we could have a horizontal reflection, or we could say we don't have. There's different options. So we can have a horizontal reflection or not, either one. Therefore, b can be positive or negative. So b equals, remember b is the reciprocal of the horizontal stretch factor. So either b is 4, or you could say that b is negative 4. Either one, get the same answer in this case. And then translation, if we look at the vertex of the original function, it's at the point 0, 0, which would not be affected by any stretches or reflections. So then we can just look at where does this point end up on the new function to figure out what our translation values are. So we go left 7 units and up 2. which means we have a horizontal translation left 7, so h equals -7, and a vertical translation up 2, so k equals 2. Then we can write the function g of x equals a, which is 2, f bracket b, which is either 4 or -4. I'm going to go with +4, bracket x minus -7, so x plus 7, close bracket, plus 2. But if I look at the function y equals f of x, this function is the absolute value of x. Absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2. On the negative side, absolute value of -1 is +1, absolute value of -2 is +2, and so on. So I can write f of x equals absolute value of x. Then I can write g of x more specifically as 2. Instead of f, we're going to put absolute value, 4 or -4, x plus 7, close bracket, close the absolute value, and then plus 2. The graph of y equals g of x represents the transformation of the graph of y equals f of x. Determine the equation of g of x in the form y equals a f bracket b bracket x minus h close bracket plus k. Again, we have f of x is the original function and g of x is our transformed function. We need to start with our stretches. Vertical stretch factor. If the graphs that you're given have points on them, then what that means is that these 3 points are transformed to become these 3 points. If we don't have any points shown and there's not any like endpoints like these ones have here, we have endpoints, so we know that those points correlate on the 2 graphs. If we don't have those, then there's different options for the transformations that occurred, but if we've got points on each of our functions, then those are the transformed points from the original function to our transformed function. So vertical stretch factor, I'm going to look at the vertical distance between the lowest point and the other points that were given, which on f of x is 1 unit. And on g of x, the distance between the vertex and the other 2 points that were given is 3 units. I go from 1 unit to 3 units, which tells me that I multiply by 3. Therefore, the vertical stretch factor is 3. Then I notice I have a vertical reflection. I can tell I have a vertical reflection because the original graph opens up and the new graph opens down. Vertical reflection means that A is negative. Then putting together the vertical stretch factor and the fact that A is negative, we get A equals -3. Horizontal stretch factor, we're going to look at the distance between the 2 points that have the same y value. So in the original function from here to here, that's a distance of 2 units. And on our transformed function, we have a distance of 4 units between those points. We go from 2 units to 4 units. So we multiply by 2, which means our horizontal stretch factor is 2. Then do we have any horizontal reflection. Again, with this one, we have a symmetrical graph and the vertex is at the y-axis, so it's symmetrical about the y-axis. So if we reflected it across the y-axis, we would have the exact same graph. So again, we can say that we can have a horizontal reflection or not. So B can be positive or negative. It's your choice. And then putting that together with the horizontal stretch factor, remember B is the reciprocal of the horizontal stretch factor. Therefore, B equals either positive 1/2, or we could have B equals negative 1/2. And then doing our translations, the original function also has a vertex at 0, 0, so that's not going to be affected by any stretches or reflections. So then we can look at where it's translated to get our horizontal and vertical translation, which is right 3 and down 4. Then our horizontal translation, we go right 3 units. Therefore, H equals 3. And our vertical translation, we go down 4 units. Therefore, K is negative 4. And then we can write the function g of x equals a, which is negative 3f bracket b, which is either positive or negative 1/2. I'm going to go with positive. And then x minus 3, close bracket, close bracket. That should not say minus k, that should say minus 4. And then minus 4 outside the brackets. But I should be able to recognize that my original function, f of x, is y equals x squared, the base quadratic function. So this is f of x equals x squared. Then I can write g of x equals negative 3. No more f because I'm going to put x squared in. So bracket 1/2 bracket x minus 3, close bracket, then squared minus 4. Sketching transformations. When sketching transformations of a function, remember your order of operations. We have to stretch, then reflect, and then translate. Example, the graph of the function y equals f of x is given. Sketch the graph of y minus 1 equals f of negative 2x plus 6. We should notice that the brackets are not factored, so we need to do that. I'm also going to move the negative 1 over by adding 1 to both sides. Then I get y equals f of negative 2 bracket x minus 3 when I divide 6 by negative 2, close bracket, and then plus 1. So I have b equals negative 2, which means we have a horizontal stretch factor of the reciprocal of the absolute value of b, 1 over absolute value of b, which equals 1 over 2. So our horizontal stretch factor is 1/2. And because b is negative, we also have reflection horizontally, which is across the y-axis. we have an h value equal to positive 3, which means that we move right 3 units. And we have k equals 1, so we move up 1 unit. So we can apply all of these transformations to the graph one by one and end up with our transformed function, or we can use mapping notation, apply that to each of our points, and get the new points. A point xy on the original function transforms to the point x divided by b plus h and a times y plus k. The x value we could also write as 1 over b times x plus h. Then we have the point xy on the original function becomes x divided by b is -2 plus h, which is 3, and then a is 1, so just y plus 1 for k. Then we can transform each of our points. Let's label our points. This we'll call point A, which is at x equals -6, and y is +3. This one is point B, which is at x is -4 and y is at -3. This point we will call point C. It is at 0, 0. And this point we'll call D, and it is at x equals 4, y equals -4. Then the point -6, +3 becomes -6 divide -2 plus 3 and 3 plus 1. -6 divided by -2 is +3 plus 3, and then 3 plus 1 is 4. So we get the point A prime, which is 6, 4. And we can plot that point. X equals 6, y equals 4 is right here, and that's point A prime. Then point B, which is -4, -3, goes to -4 divide -2 plus 3 and -3 plus 1, which is -4 divide -2 is +2 plus 3, -3 plus 1 is -2. So we get the point B prime. 2 plus 3 is 5, and -2 for the y value. X equals 5, y equals -2. That is B prime. Point C, which is 0, 0, goes to the point 0 divide -2 plus 3 and 0 plus 1, which becomes the point C prime, which is 3, 1. X equals 3, y equals 1. C prime is here. Then the point D, which should be +4, -4. So D 4, -4 goes to the point 4 divide -2 plus 3 and -4 plus 1. 4 divided by -2 is -2 plus 3, -4 plus 1 is -3. That gives us the point D prime, which is 1, -3. Plot that point. 1, -3 is here. That's D prime. Then join A prime to B prime. B B prime to C prime, and C prime to D prime. And there's the graph of our transformed function. The graph of the function f of x equals absolute value of x is stretched horizontally by a factor of 1/2, so horizontal stretch factor of 1/2, which means that b equals 2, the reciprocal of the horizontal stretch factor. Then it's reflected about the y-axis. That's a horizontal reflection. So b is negative, which means that our b value is -2. And then it's translated 6 units to the left, which means h equals -6. H equals -6, and 3 units down, so k is -3, to form the transformed function g of x. Determine the simplified equation of g of x in the form y equals a absolute value x minus h plus k. Notice that we don't have a b value. But we do have a horizontal stretch factor. So what this is saying is we want to convert our horizontal stretch factor and reflection to a vertical stretch factor. So let's write the equation with b first. So we'd have y equals a is just 1, so nothing for a at the moment. Then we have absolute value, the b is -2, bracket, x minus h, so x minus -6, which is x plus 6, close the bracket, close the absolute value, and then plus k, which is -3. Now we want to be able to bring this part outside of the absolute value so that it becomes an a value instead of a b value. We can write this as y equals absolute value of -2 times the absolute value of x plus 6, and then -3. Then y equals absolute value of -2 is 2, and then we have absolute value x plus 6, close the absolute value, -3. So there is this function written with an a value instead of a b value. And we can use our graphing calculator to help us double check and see how these two functions are the same. Go to y equals, clear what we have. We want the first one, which has the b value, so absolute value of -2, bracket, x plus 6, close bracket, move out of the absolute value, and then -3. We can graph that, and here's what we get. Then go back to y equals, and in y2, enter the second equation, which has an a value instead of a b value. It's 2, and then absolute value of x plus 6, move out of the absolute value, and then -3, graph that, and you'll notice that now we have a red graph in the same spot that we had the blue graph. So if I turn off the red graph and graph again, I see the blue graph. I go back, turn back on the red graph, and I see the red graph. So these two graphs are exactly the same. So we see that we can have the same function represented by different transformations and then by different equations. So this one was a horizontal stretch factor of 1/2, a reflection across the y-axis and translation 6 left and 3 down, whereas this one, which gives us the same exact graph, is a vertical stretch factor of 2. We don't have any reflection anymore, and we have translation 6 left and 3 down. And both of those represent the same function and the same graph. They're just written in different ways, so they show different parameters and different transformations. That brings us to the end of Chapter 1, Lesson 5.